So this is exercise 2.3 that we're looking at now on page 84, and I guess the first thing we always do with these projects is we draw a diagram, see if we can understand what's going on. So here it's a pumping out test, so we've got effectively this is our sort of ground level, okay, and then we're told that the bed of sand is 12.5 meters thick. So if we say this is all sand, and this is, you know, the actual thickness of this is 12.5 meters, and the pumping out test is done. So this is an impermeable strata down here. So a well has been dug into the sand, and basically water's been pumped out of this at some kind of flow rate or an amount of flow, and the water table would have been higher, presumably maybe up here somewhere. That would have been the water table, and we're told, or we draw it first of all, but then we sort of read through where actually was the water table. It was 1.95 meters below ground level. So there was a particular period of time at the beginning when this water table was at 1.95 meters below ground level. So water's been extracted from this well, and over time that would have pulled the water table down to another level. We don't exactly know how far, but we'll read about that in a minute. And so some observation wells have been dug. So an observation well was put in here, for example, and then maybe another one here. And the water level would have been recorded in these at a depth. Okay, and we're told after some time the discharge was constant, and it was down to 850 kilograms per minute was coming out of that well, and then the drawdowns, i.e. the amount that it was drawn down by in these particular wells, the drawdown was 1.625. It's going to get a little bit busy, this diagram here, but the drawdown, we'll call this one 1.625, and the drawdown in there, just draw it in there, was 1.36. We're also told what the distance is these wells are away from the original well, and they were at a distance of 15.2 meters and a distance of 30.4 meters. And on this test then, what we're trying to find out is what is the coefficient of permeability. Coefficient permeability K. And that's effectively a velocity, it's meters per second. It's the units. And so there we have got all the information that we need to work it out. Now if we go earlier on in the actual textbook itself and try and work out what the equation is for this, we would have to dig that out from the actual notes itself earlier on in the textbook, okay, and come up with a value for what K is. You know, and to cut a long story short, the coefficient of K is found by an equation with Q times the natural log of R2 R1 all divided by pi Z2 squared minus Z1 squared. That's the equation that we need to work with. And so our job is just to find out what is Q. Well, Q is 850 kilograms per minute. That doesn't look like the sort of units that we like. Ultimately, we're going to want an answer in meters per second. So this needs to be converted to effectively how many cubic meters per second. So that needs to become into meters cubed per second somehow. So that's a task we're going to have to do in a minute. I'll come back to that. R2, that's the radius, that's 30.4 meters. R1 is 15.2 meters. And then Z1 and Z2 that represents, if you look at the diagram for this equation, Z1 is this distance here. That is Z1, and this here is Z2. And so it's the distance from the permeable or impermeable boundary up to the drawdown water level. So our original water table was to 1.95 metres below the surface, and then we drew it down more. So the original water table would have been at 12.5 metres less 1.95. That will be the original, that would be the height of the water table originally. And then we subtract from that a further 1.625. Same thing for 12.5 minus 1.95, original water table, and then we reduce from here 1.360. And so we've got here all the information that can then be plugged into that equation to find out what K is. And that bit really, we've done the hard bit. The rest of it is just simply plugging the right numbers into the calculator. There's a bit of issue regarding that, which we need to be careful of the units. But apart from that, we're really on the straight run home really. I won't solve that for you. That's your job, but you should get the answer here in meters per second. And I think what we should even do before we even start these sort of problems, or before we even start to put the numbers in, is to estimate. What is the answer? What is an estimate before we even start? We know it's sand, and in Smith's book there's some tables of typical K values or permeabilities for sand. So we should guess that to an order of magnitude before we even start. And hopefully you'll get a number which comes out quite similar to what the actual answer is. So good success with that, and I hope you get the right answer.